Okay, just going on to the second and third pieces of this week's content. I would suggest don't binge them all at once. It's a lot. And if we were doing an on-campus lecture, I would probably have to do it all in an hour, and it would be pretty intense and condensed, and it's a lot to take in. So I've been making that point about active listening. So remember, you are, from a constructivist reference perspective, you are constructing new knowledge out of these experiences. So take notes, make sure the video is the only thing you're watching, etc. I won't hammer that every single week, but it's quite important if you want to actually retain this stuff. So the two concepts quickly. One is conceptual change theory, which is one particular constructivist referenced approach to teaching sciences in particular, and inquiry learning, which is a very influential concept in teaching science. If you look at the senior science, that old tongue twister, senior secondary science syllabuses, you will discover that inquiry learning is quite upfront. It's in the first couple of pages, there's a big blurb about inquiry learning. So it is the model that underlies the syllabus documents, so we need to understand it. So I'll talk a little bit about those two things. Conceptual change, students, as I said, are not blank slates, empty cups, etc. They come with some concept, usually about particular things, unless it's something that they don't encounter at all in their everyday life. So students typically don't come to class with an atomic theory of matter. Although, since about year 4, they've probably been talking about a particle theory. So they probably have this idea that there are tiny particles in the air and the water and everything around us, and that they vibrate and that they explain the behavior of solids, liquids, and gases. They probably have something. They probably don't know about protons, neutrons, and electrons, although they might have watched science shows and have some of that. It partly depends on who their parents are, whether their parents take them to science centers and museums and so on, whether their parents have these conversations with them, what they watch, read, consume at home, etc., etc. So each student will have a lot of different knowledge, a lot of different experiences and background. And typically, so for things like motion, for example, they will have thrown and caught a ball, in my case, very badly, but they will have played some kind of sport, even if just for fun in the park. They will have ridden a bike or a skateboard or a balance bike or a tricycle or something. They will have traveled in cars and trains, buses, planes, whatever. So they have a repertoire of like embodied knowledge of physics in the real world. Sciences in the real world. They live in bodies. They have some sense of biology and germs and sickness and being sick and so on. They have some understanding of chemistry. They eat food. They use various things to do various things. You get what I'm saying, that students don't come empty of concepts. They have a lot of experiences and they've tried to make sense of it because, again, George Kelly suggests that humans are trying to make sense of the world. It's one of the things that we inherently do as humans is try to pattern match, to recognize, to make understand. So typically when we're teaching a new concept, there are a range of things that we're doing. If it's something that they really have no concept about, so if it's the standard model of particle physics, which is now actually part of secondary, it used to be part of university, but the standard model, bosons, mesons, leptons, the flavors of quarks and so on. And apologies for everybody that leaves behind. That's something that you don't pick up in everyday life. You might hear quarks if you watch The Big Bang Theory or something like that, or quarks depending where you went to university. Typically that is conceptual development. We call that conceptual development where they don't actually have anything and you're developing it from the ground up. And that's what constructivism typically is kind of understood as, kind of empty block. Maybe you needed to grade the block or add some fill or a retaining wall, but basically flat block, you're constructing a concept from the ground up. Posner, Strike, Houston, and Gerzog, their names appear in a couple of slides, who developed this, said, no, it's most often not like that. It sometimes is. So sometimes they do conceptual development, but sometimes you need to do conceptual change. They have an existing concept and you want them to move off that concept because it doesn't work, because it's not scientific, because it works only in some examples or in some contexts and not everywhere, and so on. So you want them to move off their existing concept and onto a new concept. And that's conceptual change. You're switching from one to the other. And that quite often is what we're doing in science education. We're switching a student from a non-scientific or unscientific concept onto a scientific concept. And we hope that the students will then take that scientific concept and use it to explain the world. Because that's what science really is for, explaining our experiences of the world. So that's what we're hoping to do in science education. There are a number of languages used for these existing concepts that we're trying to move students away from. So misconceptions has been used quite a lot in physics and chemistry, but there's a number of terms. So misconceptions, so we have a correct scientific conception and the related misconception. So what's a good example? Combustion. There was an old concept called phlogiston theory. If you've seen my email signature that I send from my phone, it says something about phlogiston. The idea was that phlogiston is in substances and it escapes when you burn it. So you're burning out the phlogiston. And that theory was used for quite a long time to explain combustion. But when Dalton and others started doing very careful experiments in which they captured all of the gases and everything from combustion, they discovered that in fact the system gets heavier. If you capture all of the smoke and all of the ash and all of the everything, when you burn a piece of wood, you end up with a mass greater than the original mass of the wood. And that didn't seem to make sense because you got rid of the phlogiston and now it's heavier. So they thought for a while that phlogiston might have negative mass, but that's kind of hard to maintain. And around about the same time, Lavoisier and Dalton and others discovered the existence of oxygen in the air. So it made sense to understand combustion as combining of some kind of fuel, coal or wood or whatever it happens to be, with oxygen from the air in combustion. And so the overall mass increases because you've now added some oxygen. So you can see that phlogiston theory is the misconception. It's an unscientific idea. It doesn't really work if you do a proper careful experiment. Combustion theory with oxygen is a scientific idea because it works in whatever context you want to use it. And it also explains things like rusting, which is like slow burning, but it's still a combination with oxygen and so on. So do you get this concept? So this idea of a misconception is an idea that doesn't well explain the rest of our experience. I could talk about Aristotelian concepts of physics, but maybe that's too long an example because this is going to end up being a longish week anyway. But there's been other languages, so misconceptions, preconceptions. There was a bit of a feeling in the field that misconceptions was like judgmental. We're saying that they're scientists, students, your knowledge is bad. Come take our good scientific knowledge, which was kind of considered to be not cool. So they decided, all right, we'll call it preconceptions. It's just the concepts that they have before they get to us and we teach them. Or children's science. So Gunston and White and Osborne talked about children's science. How are children, kind of honouring the ways children have been trying to make sense of their lives so far. Alternative conceptions or naive conceptions, there's a number of languages, but misconceptions is probably still the most common. And if you go looking for common misconceptions, so just Google common misconceptions about the topic that you're going to teach next, and you will usually find some lists, including ones in particular research papers. When you do your, let me see, I've got to be a little bit careful. The assignment in the master's course, the first assignment for the master's students, bachelor's students, just ignore this for a minute, asks you to critique a piece of text from a textbook. And one of the ways you might critique it is in terms of the misconceptions that it gets rid of or doesn't get rid of or accidentally includes and so on. So that's just a kind of a small assessment hint. But this idea of misconceptions and moving students on from the misconception to the correct conception. We try and avoid doing indoctrination in science education. We don't want them to just, I'm telling you, I'm a science guy, trust me, that's it. What we want them to do is understand the world, the physical world. And so if a scientific concept is for explaining the world around them, then what we want them to do is test it against the world. So ideally, more labs, more demos, more real world stuff, so that they have this visceral sense of what actually a concept is good for, how it explains the world. Hopefully that's helpful. Posner, Strike, Houston, and Gerzog said that for conceptual change to occur, okay, small digression. They used a metaphor which is wing walking. I don't know if you've seen this. In the old black and white movies, you would have a biplane, so two wings with a whole bunch of struts between them and so on. And stuntmen and women indeed, would be on the wing of the plane while the plane was flying. And when you're doing that, you're hanging onto a strut. And if you want to move to a different place, you want to, all right, let me narrow my grasp a bit. You want to grab a new strut and have a really good solid firm grip on it before you let go of the old strut, because you are hundreds of feet above the ground and traveling at probably 80 miles an hour, 100 miles an hour. I'm using old terms because it's old stuff, 160 kilometers an hour. So if you don't have a good grasp, you're going to end up falling off the wing, which is bad. So wing walkers don't let go of the old strut until they've got a really firm grip on the new strut. And this metaphor works for students. They're not going to let go of the old concept that served them well many days through their life until they feel that they've got a really firm grip of the new concept and that it's better and more powerful. So you need dissatisfaction with the old concept. I haven't put it on this slide, so make a note of it right now because it will be in the quiz. There'll be 4 things that you need for conceptual change. First one is dissatisfaction. In some way, you have to demonstrate to the students this concept no longer explains your experience. You do an experiment or you do something that says, all right, your theory, your existing concept predicts that will happen, but in fact this happens, so you should be dissatisfied with your existing theory, your existing concept. And then the new concept that we're offering to them as an alternative has to be intelligible. That is, they have to be able to understand it. If they can't understand it, they're not going to adopt it. That kind of makes sense. It has to be plausible. It has to feel right. It has to have a good vibe about it. It has to be believable. And that's usually okay, although for some of the stuff in relativity and some of the stuff in quantum, where it's quite counterintuitive and weird, that can be harder. But by that time, usually we've got them trusting us a bit because they've seen a number of things we've done already. So intelligible, able to be understood, plausible, seem real, seem reasonable, seem sensible, and fruitful. That is, it has to have the opportunity, have the potential to explain more, to be more powerful, to explain more phenomena that their existing concept didn't explain. So that 4 things: dissatisfaction, intelligible, plausible, fruitful. That's the root of conceptual change theory in 4 things. And it's a really interesting paper, Posner, Strike, Houston, and Gerzog, 1982. They drew on philosophy of science, and I won't get into that now because it's a little bit more than we've got time for. But it's quite nice, and it actually takes constructivism and turns it into an approach for teaching, an approach for understanding the decisions we make when we're teaching. It's not a stage theory and it's not a teaching sequence. It's not, okay, first make them dissatisfied, then make the new thing intelligible, then make it plausible, then make it fruitful. It doesn't work that way. It's for drawing the teacher's attention to the concept of what you're trying to do here. You're trying not to build something from scratch on an open field. You're trying to get them to switch from one concept to the other. I think I went the other way last time. So you're trying to get them to adopt the scientific concept because it is more powerful, because it really does explain their experience better than their existing concept. One strategy, teaching strategy, that we can develop based on this is predict, observe, explain. Ask the student to predict what will happen in an experiment, then observe what does happen, and then ask the student to explain what happened and why it happened, and to check whether their existing concept explained or didn't explain what they were looking for. So dropping 2 objects of different masses but similar sizes is the common example. Many will predict that the heavier one will hit the ground first. In fact, if the experiment works right, they hit the ground at the same time. So they predict They observe, they explain why what they had predicted wasn't explained by the existing theory. This is part of establishing dissatisfaction, to test their existing concept. You can add an extra step, actually: predict, explain, observe, explain. It's a way of getting to their prior knowledge in a rich way, because you get them to say, I believe that the heavier object will hit the ground first because, give me an explanation, because I have seen this kind of thing happen in my life. I've seen, a shot put is going to hit the ground before a baseball, and so on. A shot, I guess. And then get them to observe, and then get them to explain. Interesting side note on this is that people observe what they expect to observe. So you actually may have to slow down the video or do something, because actually just doing this experiment, the students who predict that the heavier object will land first will see the heavier object land first, while the students who predict that they'll land at the same time will see them land at the same time in the same experiment. Because in some way our concept almost conditions our experience of the world. So it's actually quite challenging to create that dissatisfaction, because concepts are resistant to change. They're resistant to challenge. So that's just a kind of a caveat in trying to do this, in trying to teach them in this way. And that's the second part of predict, observe, explain. And bottom point there, a well-designed experiment, the scientific concept is better. It's more full, it's more clear, it's more powerful, it's more, intelligent, intelligible, plausible, and fruitful than the naive conception. And in the class, there might be 4 different naive conceptions or misconceptions. It won't necessarily all be the same one. But there's not an infinite range. There's not as many misconceptions as there are students. There are a number of common ones. And understanding those as you become a more experienced teacher is quite helpful as well. Talked about evidence, but real experiments over telling them or over showing them a video from far away tend to be more powerful. And I said this before, I think more experiments, the more you can do, the better. And even if it's just a demo that you bring something to class, if you're not timetabled in the science lab or whatever, but you show them something real that the scientific concept explains, is more powerful than just telling them and having them write down the scientific concept. Okay, so that's conceptual change. It's quite a powerful concept, and it's a way of thinking about teaching and a way of thinking about how students learn that maybe wasn't intuitive, maybe wasn't obvious to you, maybe it was. Maybe that's how you already thought about how students learn. But I suspect at least some of you thought that it was much more about conceptual development than about conceptual change. Okay, switching topics briefly. Inquiry learning. Inquiry learning is not constructivist, it's constructivist referenced. And I talked about that before on the constructivism vid, so I won't belabor the point. It's consistent with the constructivist theory of knowledge. This is a concept that I think is original to me. I don't think I've heard it anywhere else. It's the idea of open-ended versus open-entry inquiry. Basically, there are 2 possible kinds of inquiry that can happen. One is if you have a scientific concept. If you want the students to learn a scientific concept, then what you actually want is open entry inquiry. You want a wide range of questions at the start, wide range of perspectives. You want all the misconceptions. You want them to be out there on the table and discussed and so on. But over time, with experiments, with teaching, with learning, you want them to all end up at the same place. You want the students to understand the canonical, correct, accurate, workable, best we currently have scientific concept, because they have to pass an exam, which is the trivial reason, but because it's powerful for explaining experience, which is the real reason. But in teaching science, you do not want to start open and end up with 2 competing explanations, which the students then take away for the rest of their lives, and one of them is going to be wrong, because the scientific one is the best one we have, so all the others are going to be less than the best one we have. So for scientific concept learning, open entry, closed end, or closed onto a single thing end. You want them to learn the scientific concept. For socio-scientific issues, So for issues like, should we use nuclear power as part of our power mix in Australia? There are a very wide range of possible answers that we could use. There is scientific knowledge that's relevant. So you need to know about half-lives, you need to know about types of reactors, you need to know about safety precautions, and you need to know about nuclear waste, the kinds of waste that are produced, how long it lasts, how it needs to be stored, etc. So there's a bunch of science, but there's also a bunch of economic. Are they economically viable? Are they too expensive? Would they take too long to build to really be useful? There's a bunch of, people won't want it in their backyard. People are scared of it after watching the Chernobyl documentary and seeing the Fukushima coverage and so on. And so on. So you start open, you start wide, and there's a range of valid conclusions to come to because the answer is not scientific, it's socio-scientific, and people will have different values on different things. So some people will be more worried about the radioactive waste and how long we have to store it. Others will be more worried about, is this a better replacement for coal, for example, because it doesn't produce greenhouse gases? And is it more viable and more reliable day and night, windy, not windy, sunny, not sunny, than renewables? Maybe, maybe not. Maybe renewables plus storage, etc. But you can see what I mean. There's a range of possible valid positions to take. We might disagree about them, but they're not. We can't say that they're categorically wrong. They're different because they're different value positions. So for socio-scientific issues, open entry, open-ended. For scientific concepts, open entry, down to the correct concept. Is that clear? I hope it's a useful concept, because I hear, unfortunately, sometimes teachers will say, oh, there's no right answers in science. It's all about your own perspective. It's like, no, wrong, bad. There definitely are right answers in science. But on the other hand, you could also, as a teacher, be way too dogmatic and say, no, we definitely should have nuclear and there's no arguments against it. Well, that's also not appropriate. So hopefully that's helpful. Inquiries about questions and who asks the questions and who owns the questions. Do the students come up with the question themselves? Do the students come to own the question and decide that that's something that they want to, that they want to investigate and explore? Or does it always remain the teacher's question that the students are just complying with? Hopefully the students own it in some sense, that the inquiry, that it's their inquiry, that they care about the solution and the ending. When I was talking about planning, about the story arc of a unit plan. So you've got a beginning, a middle, and an end in the unit plan. That's one of the things that can help the students to own the question, because the beginning and the middle and the end, hopefully, the end might be answers. The beginning and the middle are probably questions, probably things that they want to know about, things that they're inquiring into. In developing a new concept, particularly if the students are developing the concept among themselves in a small group or as individuals working with experiments, they will develop the concept, but they won't necessarily develop scientific language for it. So they might have a push or a pull as a word. So there's a push acting in this direction. They won't necessarily come up with the word force to describe that. So the teacher's role is to help provide them with that scientific language, that literacy of science, so that they understand that there's a term called force, there's a term called mass that's different from weight, those kind of language terms, that they use language carefully and in scientific ways. And as I say, that's not something that they're going to construct for themselves by experiment. That's something that they learn as we teach it to them. Kinds of evidence, I keep hammering this: real world experiments, real world evidence is valuable. Library evidence is important, and in the assessment tasks in the new senior syllabuses, they're asked to do a student experiment, which they have to do real world experiments, create primary data, and they're asked to do a student investigation in which they're asked to go to the literature and get secondary data. So they have to do both of these things to develop their concepts. Inquiry basically can be understood as meaning, oh, well, you're on your own, kids, just go. Just throw you in the deep end, here's some apparatus, figure it out for yourselves. It's clearly not that. Doing good inquiry teaching involves being really actively engaged with the students, their questions, knowing where they're up to, what the pain points are, where they're going, do they own the question, are they on topic, are they off topic, and so on. So you're very, very actively engaged as a teacher in inquiry teaching. We scaffold, we ask the questions, we scaffold them into the skills as well. I think the scientific inquiry processes are complicated and challenging, and doing that properly requires scaffolding and development. You know, the scaffolding is a metaphor around constructivism as well, that you put the scaffolding up outside to allow you to build the building, and then you take the scaffolding away when the building can stand by itself. So we scaffold to support the students as they develop the skills, and then once they have the skills, we take our scaffolding and support away, and they inquire in their own right. So we're developing these skills in collecting, analyzing, and interpreting data. How to draw a graph. We don't just assume that they'll understand what goes on which axis and how to create a scale and all of that kind of stuff. These are skills that we help them build up. The last piece is managing arousal. It sounds a bit wrong, but it basically is psychological arousal. It's the way in which students are engaging with things. And it goes back to my hand gestures about the zone of proximal development again. If they're not being challenged, if they're down in this zone where they can already do it easily by themselves and not learning anything new, then their arousal will be low because they'll be bored, they will be disengaged because there's no prospect of learning. If they are up here where they can't possibly do it, where they're stuck, lost, have no idea what's going on, they also will be disengaged. So as you're the teacher, you're wandering around the different groups doing their activities, and you're listening in. You know whether that group has stopped because it's too hard and they're stuck, and you can give them some information or ask a question that directs them to some information, or give them a prod and a nudge in some other way. And you can know whether that group's off topic because they're bored and it was too easy, and you can challenge them with harder questions and so on. So you're managing that all the time. Some level of frustration. So it's like playing a game on the computer. If it's really super easy and you're just grinding, doing the same easy thing over and over again, it's really boring. If you're doing an impossible battle over and over again, it's equally boring, or you rage quit and you've had enough. It's in that zone of just being challenged to build your skills that it's actually fun to play. And it's the same in school, that it's fun to play when you're in that zone. Okay, that's been a quick run through of conceptual change theory and inquiry learning. It is a longish day, and there are two more pieces, explanation, teacher explanation, and teacher expertise, and they'll be pretty quick, and I'll talk about those in the next video. See you shortly.